In this episode, we're going to cover several linked list operations from a high level, and you're gonna implement these for the homework assignment. So this is the list of operations that you'll build for the homework. In the real world, there are other operations that you'd likely want, but for our purposes here, this list should suffice. So init makes a new list. Report is a debugging function that will print out contents of a list. Append is going to add data to the end of the list, while insert places data at a particular offset. Size gets the size of the list. Contains checks to see if the list has a specific value. Get value at offset gets a value if the offset is valid. And remove changes the list so it no longer contains specific data. Okay, so in order, let's initialize an empty list. So remember this drawing of an empty list? If we need an empty list, all we have to do is initialize a linked list reference to be null. Here it's called start. If you need a new linked list node that has a particular value, use an init list function like this. So thinking about preconditions, do we want to have any limitations on the input data? In our case, it doesn't really matter. Any number is okay. So what about postconditions? Well, the most obvious one is that we've initialized a node with the given data and returned it. Can you think of anything else? I'm not thinking of anything. Okay, so drawing out the init list code as a diagram, it might look like this. So the next reference should be null. So it seems obvious when we have a picture like this. So we're making a new node, we put some data in it, and the next reference has to explicitly be set to null. Okay, append. So now we're getting into more interesting territory. The append function looks like this. It takes a linked list and some data that we want to apply to it. And it also returns a linked list. Okay, so why is that? This and the other functions that mutate the list structure are going to return a reference to the first node of the linked list after the operation is completed. And this is needed in the way that we're doing this because the mutation might actually change which node is the first node. So for example, if we append data to an empty linked list, we need a way to refer to that first node after the append function completes. So we return a reference to it. The input list value is null because it doesn't have anything in it. And once we've made our one node list inside the function, the only way for that reference to be useful is if we return it. From there, it's the calling context's job to update the reference. So we need to store the return value from the append function. If you're used to an object-oriented approach and this seems weird to you, don't worry. It actually is kind of weird. This is just one possible way of working with data structures. We'll change it up throughout the course to use different approaches, like with container objects or maybe even classes. If the input isn't null, then we have to find the end of a list. So we'll initialize a node like we've talked about, and we'll have the end of the list refer to it. And always remember that you have to return a reference to the first node in the list. When we insert data, we're given the list and data as before, but also an offset. We're going to make a new node that will be placed into the list so that it lives at the given offset after the process is all done. And then we'll return the start of the list, which might be different if the offset happened to have been 0. You're going to need to develop the skill for drawing the operations in diagram form. So you're going to need to identify various cases, like how to handle empty lists, or what to do when the offset is 0, or something else. Here's one possible case where the list has some data in it, and we need to place new data at some non-zero offset. I'm showing you handmade drawings here as a subversive attempt to make it easier for you to do. I know some people have a hard time putting pencil to paper, but really just go for it. I'm sure you can do it. So draw a picture of the state of the list to start with. Then, on paper, try to work within the rules to transform that initial state into the one that you want. In this example, we want a node with a value 42 to end up at offset 1. So draw a new node, and in code, you'll make this with the initialize function, sort of near where it should go. Now, looking at this, you can see you'll need to adjust the reference at the previous offset to refer to your new node. Every time you make a new box or move an arrow, that's going to correspond to some code that you have to write. If you've annotated the sketch with things like the offset, also remember to adjust those if the situation changes as it does here. So size. I'm going to speed things up here because my goal is to give you some practice in making your own drawings. I'll show what I did, but not necessarily talk it out. The size function just counts the number of elements that are accessible from the starting node and returns that number. The contains function returns true if any accessible nodes in the list have the given value, and false if they don't. The getValue function is sort of like an indexed access in a traditional list or array, and it's often written with the square brackets like some list sub I. This isn't that syntax though, but it's similar. Our links don't have that syntax, but we can write a function for it. It takes an offset, and all we have to do is zip along a list of that many steps. If we can't, like if the list isn't long enough or if the given offset is negative, the documentation just says to return the special not a number value, NaN. There are a few use cases for removing data. The first case is that we want to remove the very first node at offset 0, which means the return value will be to a different value than what was passed in. The second case is that we want to remove the very last node. This just means that we scan to the end and set the second to last node to point to null. The third case is the generalized case where we're asked to remove a node based on an offset. So you might consider letting this function do the work for the other two if you want to. The trick is just to send in the right offset. Be careful that you return a reference to whatever the first node in the list should be. What should you do if the list is now empty? How do we model an empty list? Well, with null in this case. This episode has been sort of a graphical, sketch-based tour of how you might depict your data structure in different operations like inserting and removing data. I took the time to do a full episode on this because from experience, it seems to me that students who learn to make sketches, that they help them reason about what's going on, and they tend to get way, way more out of this class. So now that I've gone into some detail on that, the next thing is to translate those sketches into code. We'll cover a few of the operations that you'll need for the homework, at least some of the little patterns that will help you get to the finish line.